In this section, we're going to be going over continuity. So we noticed before that when we are finding certain limits, we can do direct substitution and find them by just evaluating f of a. And when functions have this property, that means they're called continuous at a. So the definition of continuity at a number: a function f is continuous at a number a if the limit of f of x as x approaches a equals f of a. So once again, that is just direct substitution, and when we can do that, we say that it's continuous at that number a. So there's three things that need to happen here if that's going to be the case. The first thing is f of a has to be defined. So we plug in we evaluate f of a, and then we actually get a value out. Second thing is the limit of f of x as x approaches a exists. And the third thing is that the limit of f of x as x approaches a equals f of a, which is just the definition of continuity. Okay, so we can see graphically here continuity for this graph. And it's pretty obvious if something's continuous when you're looking at the graph, because we know that continuity, kind of like the bad definition of continuity, is you're able to draw the graph without picking up your pencil. Okay, so this graph right here is continuous at x equals a, because the limit as x approaches a of f of x equals f of a. Okay, so it is continuous there. We can draw it without picking up our pencil. And if f is not continuous at a, then that means the function is discontinuous at a. So let's see an example here. We have this graph shown below of the function f, and we want to know at which number is f discontinuous and why. And let's just scan this left to right and look at the x values here. So we see at x equals 1, there is a hole. And what we can say is that it's discontinuous at x equals 1 because the limit of f of x as x approaches 1 does not equal f of 1. So the limit itself exists, but the value f of 1 is undefined because there is a hole. Okay, so there's one form of discontinuity. Next one, it looks like if we keep skimming and we get to x equals 3, there's a discontinuity. And once again, we're going to say this is because the limit as x approaches 3 does not equal f of 3. And this time the reason for that is because the limit does not exist, because there is a jump discontinuity. And we know that the jump discontinuity, if we haven't said that phrase yet, that essentially just means the limit from the left does not equal the limit from the right, so we know the limit in general does not exist. Okay, next one, as we are scanning, it looks like we get to x equals 5, a discontinuity at x equals 5 here. And just like before, that's because the limit of f of x as x approaches 5 does not equal f of 5. In this case, they actually both exist. The limit as x approaches 5 is whatever this y value would be at the hole, and f of 5 would be whatever this y value for that filled in circle would be. So they're not equal, so it's discontinuous. Okay, let's do some more examples. Where are each of the following functions discontinuous? For the first one, we have f of x equals x squared minus x minus 2 over x minus 2. We know that this is a rational function. So we know that rational functions are continuous everywhere in their domain. But let's go ahead before we take a look at what we're going to do, and let's just factor the numerator. The numerator factors to x minus 2 times x plus 1 over x minus 2. The x minus 2's cancel. So this function actually equals x plus 1, but x is not allowed to equal 2 because that's what makes the denominator equal 0. So that actually tells us where it's discontinuous. It's discontinuous at x equals 2 because there is a hole at x equals 2. Another name for a hole is a removable discontinuity. So if you have a rational function, we know it's going to be discontinuous when the denominator equals 0. We could also just draw a real quick sketch of this to see what it looks like. We know x plus 1 will look something like this. It has a slope of 1, y-intercept of 1, and then we can see that there's a hole at 2, so it just does not exist at 2. Okay, and then another thing that we should say for this is, using the definition of continuity, is that the limit as x approaches 2 of f of x does not equal f of 2, and that is because we know f of 2 does not exist, or f of 2 is undefined. So typically when we're talking about discontinuity and showing something is discontinuous at a point, we should use this definition. Next one, we have f of x is a piecewise function. It's going to equal 1 over x squared when x is not 0, and then it's going to equal 1 when x is 0. So let's actually graph this one out. So this is the graph of 1 over x squared. This is technically the squared reciprocal function, technically something we should know. And then when x is equal to 0, f of x is equal to f of 0 is equal to 1. So there's a dot right there. So we can see that when we're looking at this, that it's clearly discontinuous at x equals 0. And what we would say here is that the reasoning in words is that there's an infinite discontinuity. The function goes to infinity from the left, goes to infinity from the right, discontinuous at x equals 0. And then using the definition, we would say the limit as x approaches 0 of f of x does not equal f of 0. We know f of 0 is 1 based on the piecewise function. And we know that this limit as x approaches 0 is actually infinity, because it blows up from the left and blows up from the right. Okay, so the next one, we have f of x is the piecewise function x squared minus x minus 2 over x minus 2 when x is not 2, and then it's equal to 1 when x is 2. So we should be able to graph this out, but before I graph it out, let's do it and assume that for whatever reason we can't graph it. So for this, in order to determine if this is continuous or discontinuous at this point x equals 2, we need to show that the limit as x approaches 2 equals f of 2. Right, based on our definition here. I'm going to put a question mark because we're not sure if that's the case yet. So let's go ahead and figure it out. So we know f of 2 is equal to 1 because that's given to us in the piecewise function. When x is 2, f of 2 is 1. And now we need to find the limit of f of x as x approaches 2. So the limit, I'll do this on the side, the limit of f of x as x approaches 2, this is actually going to be the limit of this first function, and that's because when x is not 2, we are using this function. So we don't care what it is at 2 exactly, we just care what it is everywhere else. So we're using the first one, and we can go ahead and evaluate this. This is the same one as before, so we can actually factor the numerator and cancel common factors. So I'm just going to skip ahead to doing that. It simplifies to x plus 1. Now we can do direct substitution. We get 3. So we get 3 on the left. 3 is not equal to 1, so this is discontinuous at x equals 2. And then we go ahead and write the definition for discontinuity there. And we should be able to graph it. So let's go ahead and graph it real quick. So if we graphed it, it would look like that. It's the the rational function which simplified to x plus 1 with a hole at x equals 2. And then we know that f of 2 equals 1, so we can see it's discontinuous at x equals 2. Okay, let's do one more of these problems before we move on. And this function here, f of x, with these double brackets around the x, if you don't know, this is something called the greatest integer function. And before I explain it, let me draw it out. Let me graph it. Okay, so what I like to do, it's gonna look like a whole bunch of like stairs, kind of. I like to start right here at the origin, so it's easy to draw. And between 0 and 1, the function equals 0, but at 1, there's an open circle, and then it jumps to the next integer. So it jumps up here, hence the name greatest integer, and then horizontal again, open circle, and then it does it again. Next integer, open circle, and then it's going to continue to do that all the way to infinity. And then it also goes in the other direction. We would have an open circle down here, filled in, and then open, filled in, and I'll do one more, open and filled in. Okay, so this is called the greatest integer function. It always looks like this. Pretty easy to draw. You just have to pretty much know this first one here, and then everything else is just repeats itself over and over and over again, and it looks like steps. So this is called the greatest integer function, and now we want to see where this is discontinuous. And we can actually see this is discontinuous at every integer, right? And we know integers are positive and negative whole numbers as well as 0. So there's jump discontinuities at every single integer. And the way that we would write this is we would say the limit as x approaches n of f of x does not equal f of n, where n is an integer. So n is any integer here. Like -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, and so on. So we could replace n here with like a 2 and say the limit as x approaches 2 of f of x does not equal f of 2, and that would be referring to this spot right here. And you could see that, let me just do a little example right here. The limit as x approaches 2 does not equal f of 2. So the limit as x approaches 2 is actually does not exist, right? Because there's the limit from the left does not equal the limit from the right. And f of 2 equals 2 because that's where the filled in circle is. Okay, so that's the greatest integer function. Just kind of put that in the back of your head for now. Okay, now on to one-sided continuity. So we say that a function is continuous from the right at a number a if the limit as x approaches a from the right of f of x equals f of a. So let's see a graph for an example of this. So let's say we have that piecewise looking function right here, and this is a. Then we can see that f of a is up here at that filled in circle, and the limit as x approaches a from the right is also going to be that same exact value. So this function would be continuous from the right. And then continuity from the left is going to be the same concept. It's going to be the limit as x approaches a from the left of f of x equals f of a. So that's going to be, I'm just going to draw the same little function here. We can see that f of a would be right here at the filled in circle. And then the limit as x approaches a from the left would be the same thing. So you can see how the graphs look almost the same, except it depends where essentially that filled in circle is going to be. Next thing is continuity over a interval. So we say that a function f is continuous on an interval if it's continuous at every number on the interval. So it's a little bit a little bit more complicated for this one. So let's see an example. Let's show that the function f of x, that is 1 minus square root of 1 minus x squared, is continuous on the interval -1 to 1. So here's the two main things that we have to show. The first thing is we have to show that it's continuous within the interval -1 to 1. So notice that we're not including the endpoints for this. All we have to do for that is show the limit of the continuity definition here. Limit of f of x as x approaches a equals f of a. For that, we're just going to use a as our value. And then the second thing is we're going to show one-sided continuity at the endpoints. So that means if we are on the interval -1 to 1, if we are looking at the endpoint -1, that means we have to be coming from the right because that's the leftmost endpoint. So that means we would have to show that the limit of f of x as x approaches -1 from the right equals f of -1. And then similarly for 1, the endpoint of 1, we have to come from the left because it's the rightmost point. So we have to show that the limit of f of x as x approaches 1 from the left equals f of 1. So let's go ahead and take a look at the first thing. We are going to say that a is between -1 and 1. It's on the interval, not including the endpoints. Then we have limit as x approaches a of f of x is going to be the limit as x approaches a, and I'm just going to plug in the function here. Okay, so now let's go ahead and use these limit laws. So using the limit laws, we know that we can rewrite this as 1 minus the limit as x approaches a, 1 minus x squared, square root of that 1 minus x squared. And then maybe going one step further, we can put the limit underneath the square root. So this is just using limit laws from a previous section. And now once we get this, what we can do is we can go ahead and plug in the a value, direct substitution, and we get 1 minus the square root of 1 minus a squared. And now we can tell that this is actually the same thing as f of a. Right? It's the same thing as f of x, except instead of all the x's, we have an a. So that is f of a. So we actually showed that this equals that, so that part is good. And let me just move this around so I have more room. Okay, all I did was just squish that up there so it fit. And now for the second thing we had to show the one-sided continuity at the endpoints. So we have two things. We have the limit as x approaches -1 from the right. And this does in fact equal f of -1. I'll leave this as a calculation for you guys. These both equal a value of 1. And same thing for the limit as x approaches 1 from the left of f of x. We're supposed to show that that equals f of 1. I'll leave that as a calculation for you guys once again. And this will also equal a value of 1. So those values did not have to be equal, they just happen to be equal. So we have check, check, and check. So since we have those three things satisfied, then that means that this function is continuous over that interval. So that's how it is for most of the time with these questions. You just have to use a generic x approaches a for the first one, use limit laws, and show that it equals f of a. And then the other ones, the other two here, you have to show that it's continuous at the endpoints, which means you're using the continuity definition again. Okay, next thing we have a couple of theorems. So if f and g are continuous at a and c is a constant, then these functions are also continuous. So if you add two functions together, the result is going to give you a continuous function. If you subtract two continuous functions, the result will be continuous. If you multiply a continuous function by a constant, it'll still be continuous. If you multiply continuous functions together, the product will be continuous. And if you divide continuous functions, the result will be continuous, granted that g of a does not equal 0. Okay, so nothing too crazy there. And the next couple things, we have just some continuous function theorems. Any polynomial is going to be continuous for all real numbers. That's negative infinity to infinity. And just so we know going forward, we can write real numbers like I just said, negative infinity to infinity, or we can write it like that with the backbone R, capital R. That means the set of real numbers. Number 2, any rational function is continuous wherever it's defined, which means all x values except the x values that make the denominator equal 0. Sine and cosine are continuous everywhere, negative infinity to infinity, so I'll just put R again. And then for the last one, tangent functions continuous everywhere, except when cosine is 0. That is because tangent of x equals sine of x divided by cosine of x. Denominator cannot be 0. All right, and then one more kind of main thing here. The following types of functions are continuous everywhere in their domains. That's kind of the key here, because domains for some of these are different. So polynomials are continuous in their domain, which is everywhere. Rational functions are continuous everywhere except when the denominator equals 0. Root functions are continuous in their domain. Trig functions are continuous in their domain. Same with inverse trig, exponential, and logarithmic functions. Okay, let's go ahead and see some of these as an example. So on which intervals is each function continuous? First one, f of x equals x to the 100th minus 2x to the 37th plus 75. So this is a polynomial. So a couple different ways we can write this. We can just write all real numbers. We can write the capital R, the set of real numbers, or we can write negative infinity to infinity. That is interval notation. And I'll do one more. I'm going to do set builder and say it's the set of x's such that x is a member of the real numbers, an element of the real numbers. Okay, so any one of those would have been fine. And if you haven't seen this little symbol, this means is an element of or belongs to. Next one, we have this rational function g of x, which is x squared plus 2x plus 17 over x squared minus 1. So this is going to be continuous everywhere except when the denominator equals 0. So we should know that when we solve x squared minus 1 equals 0, that's going to give us x equals negative 1 and x equals positive 1, so plus or minus 1. So I'm going to do interval notation for this, and I'm going to say it's continuous on the interval notation from negative infinity to negative 1 union negative 1 to 1 union 1 to infinity. So notice that there's parentheses on them, so we're not including negative 1 and we're not including 1. That's all that essentially means. Everything except for negative 1 and positive 1. Okay, next one we have h of x, which is square root of x plus 1 over x minus 1 minus x plus 1 over x squared plus 1. So we have a mixture of things going on here. So we're going to use what we learned on the previous page and do each one of these separately. And for the first one here, the square root function, that is continuous over its entire domain. Its domain is 0 to infinity, including the 0, because we can't take square roots of negatives and get real numbers out. So next one, x plus 1 over x minus 1, that's a rational function. We know a rational function is continuous everywhere except when the denominator equals 0. The denominator equals 0 when x equals 1. So this is going to be continuous from negative infinity to 1, union 1 to infinity. Okay, and then the last one, that is also a rational function. So it's going to be continuous everywhere except when that denominator equals 0. And x squared plus 1 will actually never equal 0, right? Because we can't plug anything in for x. That's going to make that equal 0. So it's continuous everywhere from negative infinity to infinity. So what we're going to say now, kind of the hard part here, is how do we put this all together? And we're going to say that h of x, the function, h of x is going to be continuous over the intersection of these intervals. So intersection is the interval that is common to all of them. So we don't have to really worry about this last one because it's negative infinity to infinity. So we have to think, where do these two intervals overlap? We have 0 to infinity, and then negative infinity to 1, and 1 to infinity. So the 0 to infinity, and we can't include any of these negative numbers over here. So all we have to do is do 0 to infinity, but exclude x equals 1. So 0 to infinity, but excluding x equals 1 is going to be written as 0, 0 to 1, union 1 to infinity. So that is where that function is continuous. Okay, so a little bit harder for that one. We had to do each one separately and then find the intersection where the intervals overlapped. Next one, let's find a limit now. We're going to do the limit of sine of x over 2 plus cosine of x as x approaches pi. So before we go ahead and just plug in, we have to make sure that this is going to be continuous there, so we will be allowed to plug it in. So first we have to break it down. And when we break each one down, we have to look at sine of x, 2, and cosine of x. All three of those functions on their own are continuous for all real numbers. So next we have to do the next one, which is 2 plus cosine x. And since 2 is continuous and cosine is continuous, the sum of two continuous functions is continuous. This is going to be continuous from negative infinity to infinity. And then the last thing we need to do is the function as a whole. So notice we start one at a time and then kind of build up until we get the whole function. And we know that this is continuous from negative infinity to infinity. And hopefully you're kind of saying to yourself, well, what if 2 plus cosine of x equals 0? But 2 plus cosine of x will never equal 0. Because if we were trying to solve that for x, we would get cosine of x equals negative 2. Cosine of x will never equal negative 2 because the range is only from negative 1 to 1. Okay, so that's continuous everywhere. So since it's all continuous, we can do the direct substitution method and plug it in. So we're going to say, put a little arrow, and I'm going to say the limit as x approaches pi of this function is going to just equal pi plugged directly in. So this is the definition of continuity. Limit as x approaches a of f of x equals f of a. We plug this in and we go ahead and we simplify it. That's going to be 0 over 2 minus 1, or 2 plus negative 1. So we get a value of 0 for that limit. So kind of a long way to do it, but we had to show that it was continuous, and then we could just plug it on in. Next one, we'll go a little bit faster for this one. Find the limit as x approaches negative 2 of x cubed plus 2x squared minus 1 over 5 minus 3x. We know that this is continuous everywhere except when the denominator equals 0. That denominator equals 0 when x is equal to 5/3. So since we're not finding the limit at 5/3, we can go ahead and just plug it right in. So I'm just writing it using the continuity definition. The limit of f of x as x approaches negative 2 equals f of negative 2. And we plug it right into the function. negative 2 cubed plus 2 times negative 2 squared minus 1 over 5 minus 3 times negative 2. And we evaluate all of that. And we should get negative 1 over 11 for our answer. Okay, a few more things here. So we have another theorem with, this is going to have to deal with composite functions. So if f is continuous at b, and we know that the limit of g of x as x approaches a equals that b value, then that means the limit of f of g of x as x approaches a equals f of b. So kind of confusing with the a's and the b's and everything. Hopefully this one makes a little bit more sense. In other words, if we're doing the limit of a composite function, f of g of x, as x approaches a, what we can do is we can essentially bring that limit inside and do the limit as x approaches a of g of x, and then do f of whatever was remaining. So let's see an example here. It's easier than it looks. Let's evaluate the limit of arc sine of 1 minus the square root of x divided by 1 minus x as x approaches 1. So first, before we do anything, remember arc sine of x equals sine inverse of x. It's another way of, it's just the inverse function, another way of writing it. Okay, so what we're going to do is recognize, technically we have a composite function here. This is the outer function, this is the inner function. So what we're going to do is we're going to rewrite it using what was written above. This is going to be arc sine of the limit as x approaches 1 of 1 minus square root of x over 1 minus x. So we took the limit and kind of put it inside, and we're going to evaluate it separately. And this one's actually a little tricky. Notice that we can't just directly substitute that 1 in, because then we're going to be getting 1 minus 1 over 1 minus 1, which is 0 over 0. So I'm going to go ahead and do this on the side. What we have to do is actually use difference of squares to factor the denominator. So factoring the denominator, we want one of the factors in the denominator to be 1 minus radical x. 1 minus x can be rewritten as 1 plus radical x times 1 minus radical x. So all that is a squared minus b squared equals a plus b times a minus b. It just looks more confusing because we have a square root in there. So what happens now is we can go ahead and cancel those two common factors. We're left with the limit as x approaches 1 of 1 over 1 plus radical x. We can go ahead and directly substitute now. That's going to be 1 over 1 plus radical 1, which is 1 half. So now this is just arc sine of 1 half. And this is where you have to remember a little bit about sine inverse function. Arc sine of 1 half technically means where does sine equal 1 half on the restricted domain, negative pi over 2 to pi over 2, and the answer to that ends up being pi over 6. So I might have to go back and review a little bit with the inverse trig functions, but arc sine of 1 half equals pi over 6. Okay, so one more theorem, two more theorems, and then we'll be done. So theorem, if g is continuous at a and f is continuous at g of a, then the composite function f of g, which can be written like this, is also continuous at a. So remember, for composite functions, we can either write it like this or like this. They mean the same thing. It's read as f of g of x. So let's see some examples here. Let's see, where are the following functions continuous? H of x is sine of x squared. So if you wanted to break it down into f of g of x here, then f of x would have to be sine of x, and g of x would have to be x squared, because f of x is the outer one. So if you wanted to find f of g of x, then that's just sine of g of x, sine of x squared, which is h of x. Okay, so now we have to think when they're continuous. We know that x squared is continuous everywhere because it's a polynomial. And we also know that sine of x is continuous everywhere. So if they're both continuous everywhere, then the composite of them, h of x, is also continuous everywhere. Okay, and then the next one, I'm going to rename this one just capital, or I'll just name it h of x again. And that's just so I didn't want two g of x's. So our outer function here is the natural log function, and our inner function is 1 plus cosine x. We know that ln of x is continuous over its domain, and its domain is going to be from 0 to infinity. And we know that g of x, 1 plus cosine of x, is actually continuous everywhere, negative infinity to infinity. That's because cosine's continuous everywhere, so is 1, so the sum of them will be continuous everywhere as well. So now it's a little bit tricky. Now what we have to do is take into account that it's the ln of 1 plus cosine of x, and the ln of x is continuous over its domain. So that means ln of 1 plus cosine of x has to be continuous when this is from 0 to infinity. So what does that mean? That means it has to be positive. So for that portion, we're just using the continuity of ln of x. So now how do we figure this out? If we try to isolate cosine here, we subtract 1 on both sides and get cosine of x greater than negative 1. Well, this is almost always the case, right? Cosine is always greater than negative 1, except when cosine actually equals negative 1. That's the lowest point that it dips down to. And it equals negative 1 when x is pi, 3 pi, 5 pi, and so on, and also in the negatives. So plus or minus pi, plus or minus 3 pi, plus or minus 5 pi, and so on. So what we say is that h of x is continuous everywhere except for odd integer multiples of pi. So that's another way of writing that. Okay, so that one was a little bit harder. So one more thing, thankfully the last thing is a little bit easier, is the intermediate value theorem, which you can abbreviate as IVT. So what the intermediate value theorem tells us, that if f is continuous, so this is very important, it has to be continuous, on the interval a to b, and let's say that capital N is some number between f of a and f of b, then there has to be a number c, which is an x value, in the interval such that f of c equals n. So let's go ahead and just see what this means. I wrote right here, it states that the continuous function has to take on every intermediate value between f of a and f of b. So let's take a look at the graph. It makes a lot more sense than what it probably sounds like. So here is the curve, just this blue curve right here. And we have some y value f of a here. We have some y value f of b up here. Then that means there's some value that we're going to call capital N between f of a and f of b. So if that value exists between them, then there has to be some c value such that f of c is going to actually equal n. So basically, if there's a y value between two other y values, then there has to be an x value between those endpoints corresponding to that middle y value. So here's something that will even probably hopefully make even more sense. let's show that there is a root of the equation 4x cubed minus 6x squared plus 3x minus 2 equals 0 between 1 and 2. So we're showing that this function has an x-intercept between 1 and 2. So how do we do that? We need to use this intermediate value theorem. We need to show that f of 1 and f of 2 have different signs. So one of them is negative, one of them is positive. If one's negative and one's positive, then it had to go through 0 between them. That's the only way to go from negative to positive. So we're going to be using f of x, which is this function here on the left, and let's find f of 1. So we're going to go ahead and plug in a 1 into the function, and we evaluate that. And that gives us a value of -1. So -1, that's negative, that's less than 0. Now we're going to evaluate f of 2. So when we evaluate f of 2, we are going to assume that this is going to be positive, but we have to calculate it though. So we calculate this, we should get 12, which is positive. And now for our concluding statement here. So we're going to say, since f of x is a polynomial, which means it's continuous everywhere, and f of 1 is negative, and f of 2 is positive, then by the intermediate value theorem, there has to be a root between x equals 1 and x equals 2. Okay, so this concluding statement is very important. It should read just like that for all of these questions. We have to mention the intermediate value theorem. Okay, so that is it for this chapter.